Okay, so in this lecture, we're going to talk about and review the and particularly for the optimization. So particularly the one that we're interested in is gradient descent. So this is the most important methods in numerical optimizations. So for example, so this is coming from we need to work on the gradient and descent and you need to calculate the gradient first. I mean, in terms of gradient, we will define, and for example, if it is a function of an n variable x1 to xn, that we can define a vector x has these components of x1 to xn. So fx is written as fx as a compact form. The gradient of the function of fx evaluated at the point of xa is actually given as the following. So basically, gradient of f evaluated at xa is actually a vector of Rn, right? And although this right here is a scalar, but the gradient is a vector. So basically, it's partial derivative with respect to each component itself. So this is very important. And also, not only we can consider the function that output a vector, we can consider the function output and the previous we considered the output as scalar. We can consider the function output as a vector as well. So this is very common. For example, if you as a neural network that output the probability for each classes, that we have and say if we have m classes, then the output will be m-dimensional vectors, right, for each input. So this should be m. Okay. So that means the output could be multi-dimensional as well. So so right here, so for example, this is an fx and output is m-dimensional vector. So we can calculate something called Jacobian, which is considered as a generalization of gradient, but it's a gradient for each component of the and the vector values functions. So this is the Jacobian of the function evaluated at xa. So basically, this is a function right here. It's a function of m by n. Right, so this is important. So you can see the differences here. And if we consider just the first row, right here, so this will be the nothing but a gradient of the first component evaluate of xa. So this is, you can think about, there's a slightly differences between the Jacobian and the gradient. And you can see right here, this is actually a row vector right here. But for the gradient, by default, we usually consider this as a column vector. But still a vector, but it's like whether it's a row or column, it has a different conventions. Just Jacobian, it's more preferred to think everything in terms of rows. Okay. So these partial derivatives are often called like Jacobian and of the vector value functions. Okay, so for the scalar value functions, we can also take second order derivatives. So So we can basically think about, and taking second order, like partial derivative, that becomes a Hessian. So this is partial f, partial xi, or partial xj. And usually we know this is will be equal to, we can switch the order of partial xj or partial xi. So so this, I'm actually give you and a matrix, and this is the square matrix. It's n by n. So this is second order derivatives, and each of this is in second order derivatives, and this will be the Hessians. All right. So and that's how we and work out the Hessians here. There are a lot of like interesting optimization algorithms will take advantage of Hessian, for example, Newton's method. But in practical setup, we don't like usually use them in general because this is too expensive to calculate in general, and this will be and take too much effort. Okay, so this is gradient descent methods. This is very intuitive. So the whole idea is for the gradient descent is we trying to find the like local minimums for some functions of fx. So this is some problems we're trying to solve, which is we're trying to find out x star, that is argue mean x of fx. So this is some like optimization problems that we're trying to process. So the way we do is the following. What we do is we simply start a random vector x0. Then we compute the gradient of f at that point. Then perform a small step of opposite directions, because minus gradient of f is actually will guarantee your value, and the function value will decrease. Then repeat until it converges. So more precisely, what is that saying is, I'm going to move my xt t-1 directions a little bit toward to the gradient and minus gradient f evaluate xt-1. So this is basically the direction that you should move to, because this is tells you if you move this like a little bit, it will almost guarantee the function value will decreases. Eta here is something called learning rate or step size. We choose a like typical very small value, say 10 to the minus 3. There are more efficient variant of this algorithm, but the whole idea is very similar. But the key here is like, and for example, we just using a constant learning rate here, and of course we can change this like learning rate if we need it. Okay, so and this is basically what you will be working with. And for example, in a lot of cases in machine learning, this and gradient of f can be calculated through some an autograd like packages. So gradient f is calculated by autograd. So that means if you like, and it is a package, it can automatically calculate a gradient. So that will be like pretty straightforward. That in these cases, it will be just, this will be just evaluate at that point. Then you start to subtract the x minus alpha and multiply by the Jacobian, the gradient, and evaluate at x. So you start to like decreases until we know when it reach into the point that it's the local minimum, the point of the local minimum is the gradient of f, the norm of gradient f is small. So that means the gradient is small. That implies is around some local minimum. And the local stationary point, in fact. Some stationary point. In general, it's likely to be local minimum. So being like said, it's very likely it will be some like local minimums here. All right, so that's really good. In fact, and also, so basically, and the way that we say is, if the norm of this gradient is less than epsilon, I will stop. And otherwise, it will continue, this iterations until until we reach the maximum iteration. So this is a typical naive gradient descent. And you can see, it only take about 7 lines to actually implement that. So this is, and that's why people like to use in gradient descent a lot. It's being used again. And also, as another way, we use the constant and the learning rate. Here, empirically, we use the constant learning rate. And we can also find optimal alpha as well at each iterations. So that means alpha is changing. So basically what we do is we want to choose alpha such that it minimize this function values as much as possible. So basically it's saying I have some like function here. I know right here, I know this is direction of the function that we should be going. That means I want to find out and how much I can go such that this fx will reach as minimum as possible. Okay, and of course, if we do this, this is may be said, so that will be somewhere here that will and reach the minimum. Of course, that would be like a lot, but we don't need to do that much. But the point is we can choose a step size and very large and such that we can minimize the target function as much as possible. So this is basically, and we can turning this into new objective functions. So this is a new objective. But this is easier. So this is easier than the previous objective. So I want to compare things a little bit. So right here, so we can think about this as being a Q alpha, right? So this is a new and txt gradient of f is constant, so it's only a function of alpha here. So this is a Q alpha. And in particularly, alpha is actually a scalar, just one variables. So we are trying to find out alpha t such that argument of Q alpha. So this is a single variable. On the other hand, if we are trying to find out x star, that is argument of x of fx. So this is in Rn, and this n could be very large. So this is much more difficult problem to work with because this is high dimensional. High dimensional optimization is difficult. One dimensional, however, is much easier. Okay, So this actually can be solved by, like, say, any bisections. So that means we can set with the like domain of my alpha. Then we can using bisection search to find out optimal alpha. And if possible, just because this problem is 1D, it will be much easier to be solved. So why this is important is if we do this way, we can take much larger step size or like and the learning rate. Because you don't know whether 10 to the minus 3 is too small or too big. You don't know it. Right? So this alpha is adaptive to the problems. So basically, the local information tells you you should go this direction. We know this direction will always decrease the function values. But it didn't tell you how much that you can go, because this is actually something that is being like hidden in, information for this Q alpha right here. This is exactly the beauty of the gradient descent of the line search. All right. So in fact, we can implement that. So this is actually the optimal step size approach, and also called the line search. So it's gradient descent plus optimal line search. And I want to emphasize this only works with the gradient descent. It doesn't work out if you are trying to work with what is the and a stochastic gradient descent. So this is a simple something called like golden section search, which is a variation of bisection. You can think about bisection, but instead of you split, this into half, but instead of using like golden ratio to split. That's the and considered to be slightly better, but still like and the idea is and bisections. So you can see right here, it's very straightforward. So this is actually, I'm turning this into a Q. Q is a function of alpha. I'm using lambda to define that. So this is my lambda, and it's a function. And a function of alpha. I'm going to say my function value is between 0 and 1. So this is my interval, 0 and 1. I'm using golden section search to find out optimal alpha such that it can can decrease the and furthest as much as possible. So this is something the GSS is doing. And this is nothing but just a variation of bisections. So these are the two different lines to optimize the step size or the learning rate compared to my naive gradient descent. Everything else is the same. There's another way that we use as well. It's called Newton's methods. So this is basically says, instead I'm trying to work this directly, I'm trying to solve these problems. I'm going to solve the Hessian times V equal to the gradient of f of xa. So you solve for V first. This will be the direction that you're going to go down. Okay. So so this actually used the curvature informations. You can think about this is approximated as by the quadratic and functions and high dimensional quadratic functions. Then we're trying to solve for the and the stationary point directly. It's more likely to take a more direct route, and rather than and gradient descent because we are trying to, as I said, we're trying to fit in the whole function by a parabolas. Then you can reach to this like stationary point much faster. Usually this is and a quadratic speed compared to the linear speed. In terms of the gradient descent. So the difference is right here. It's right here. So this is we have a Hessian here. We have a gradient here. We're trying to do this solve, right? So this is basically what we are trying to do right here. That will be the direction that we should be going here. Okay, and everything else will be precisely the same. Okay, so this is something that is slightly different here. Okay, so let's try some examples. So this is some benchmark examples for optimization algorithms. So this is the first one is Rosenblatt and Bloch functions. So you can see we can calculate gradient, we can calculate Hessians explicitly. But if we actually look these functions, you can see the scale right here is from -20 to 50. The scale for this one, this is -6 to 6. Different functions and different direction has completely different scales. So the scale varies a lot. And if I'm actually plot a contour, we can see there is a valley here. It's really flat. It's down here. So you can see it right here. So this is a valley here using different color. So I have a valley here. So this is really flat. So say if you are right here, it's easy. We know we should go this way. But the issue is once we are here, the gradient will be very small. It will take forever to actually reach the and the local minimums here. So you can hear and to see the local minimum or the global minimum is and precisely as AA squared. If A equal to 1, that would just be 1 and 1. Right. So this will be the global minimum and the function value is precisely equal to 0. But if we look this 1 right here, it will be somewhere here, right? So that's why if the function looks like that, it will be very likely being trapped in this region here. Then all the gradient like descent method will be like an extremely slow. So so we can do the gradient descent right here. Right, so you have the gradient function. You know the gradient functions, in fact, and you can just simply use that. You can see, I think I put 5,000 iterations right here. At the end, it didn't converge. If you're using like naive gradient descent. So so the gradient at that point is about it's order of 10 to the -3. I'm not sure the threshold that I set. I think let me see the threshold that I set. The threshold that I set is 0.02. Yeah, I think so. I think it's 0.02. No, it's not. It's epsilon. Epsilon is 10. It's 10 to the -6. Yes, 10 to the -6. Because of the width, it's like muted here. So this is like so like epsilon, like threshold of the gradient, and the normal gradient is about 10 to the -6. So this actually hasn't reached and the threshold. The function value is about 10 to the -5. And you can see this an optimal value right here. It's close to 1, but this is not what I'm doing here. So the function value is close to 1, but not precisely equal to 1, 1. Right, but that's not really ideal. So then the difference is if we choose the optimal one, that means I'm trying to find out the optimal time step. Right? It still did 5,000 iterations, but my function is 10 to the minus 7, which is significantly smaller compared to 10 to the minus 5. And so my gradient is still like, I mean, the first component is 10 to the minus 3, the second component is 10 to the minus 5, which is quite good. And you can see my function value is even close to 1, 1 right here. So you can see this optimal and step size and optimal stepping is truly did better performances than the naive gradient descent. And we can actually plot it out. You can see this is what we are doing here. I think we also did Newtons here. It's like super impressive for Newton because if we're using Newton, it only takes 2 iterations to converge, right? So this is Newton right here. And it reached the optimal value of 1, 1. The functional value is 0, 0, and the gradient is precisely equal to 0. Just 2 iterations. It's just because everything is quadratic here, it can converge extremely fast. So you can see this is actually, a plot. We know the optimal value is right here, right? Right here. I think my initial point is, where is it? My initial point? Yeah, 0, 0, right? So 0, 0. So this is my initial point, right? For Newton, what they do is they do this step, then go this, just in 2 steps. So, and you can see this is not in the direction of the gradient at all. So this is not gradient because we are using the local curvatures and using the second order like informations here. But all the gradient, methods is going this way. But the difference is for those, they are naive gradient for and those blue points. So that's, and that means at each point they didn't go to the optimal and step size. So you can see it actually goes to this. But if we're using an optimal step size, the first one is right here compared to the naive ones. So you can see, and this one is much closer to the optimal and final and optimal values. So this is the and the global minimum. So you can see this, the first step is significantly close to the global minimum if we're using optimal and a step size with the line search compared to the naive ones. So this is the strength. And that's another function, which is more complicated. You can see this is 4th order right here. Right, we have like basically x to the 4th right here. This function has a 1 local as maximum right here, and 4 identical like local minimums. So basically has a 4 local minimums. So it looks like this. So we have a 1, 2, 3, 4. So these 4 are like local minimums, and I have 1 like and the local as maximum. So this is maximum. These are minimums. Okay, so you can see this is quite tricky. So this is highly non-convex. So this is very very complicated. So if we start with 1, 1, which is, I believe, right here, right? So this is my initial point, right here. It can go to either, can go to either ones if needed. The point of the gradient descent is we want to find out one local minimum, not all of that, not guaranteed to be global minimum. The goal is never to find the global minimum. Okay. So if we do this, we find out it will move to 3, 2, which is right here, this one, right? 3, 2, right here. The gradient is good. It's 10 to the minus 7. It takes about 613 iterations, and which is not bad. However, if we take the optimal one and to take the optimal step size, it reached the same local minimum 3 and 2, same gradient, stop 10 to the minus 7. It only take about 15 iterations. Think about this, only 15 iterations. This is significant compared to 613 iterations. This is much better because we are trying to maximize the step size as much as possible. On the other hand, if we're using Newton, in these cases, it takes about 2,000 iterations to converge. And the gradient is close to 10 to the minus 4. This is 10 to the minus 7 right here. Significant differences here. So that means Newton is not necessary better. So right here, it demonstrates Newton's method performs worse. Newton only tells you locally it will be the direction to go, but that doesn't mean Newton can always perform better. Okay? It's just being said, if you are in this region right here, like something like this, Newton can perform better because this just tells you the gradient descent converge really, really slow. It's likely being trapped in this kind of valley and this kind of banana-shaped valley. If that's the case, then Newton can do really, really good job, can reach to the local minimums extremely fast. Basically, and then within a couple of steps, it will converge. But that doesn't mean if it is more complicated landscapes like or energy and the loss functions, Newton can do and can still do better. From this, you can see this Newton is doing really, really bad job. All right. This is basically a very quick overview of vector calculus and optimizations.